In this video, I'm going to describe Little's Law and give some background on why it's important. Little's Law states that L, the number of customers in a stable system, is equal to lambda, the long-term average arrival rate, times W, the average time a customer spends in a system. So if you think about this, it makes a lot of intuitive sense that the faster people come in and the longer to stay, the more people you have. So it's very intuitive, but Little went and he proved it mathematically. He said he did a mathematical proof to show that this is indeed the case. If you may wonder, well, why is this important? And if you did an internet search on Little's Law, the top sites that come up are Lean Six Sigma sites, because Lean practitioners are very interested in this, because if you know two of the three terms, you can get the third. So it gives a very good way to estimate it. Now, different sites, depending on their focus, may use different wording for what these terms are, or they may algebraically show it differently, but it all comes down to that same basic concept. So let's think a little bit more about Little's Law. The law applies to entire systems as well as subsystems. So what's really nice about that, if you're modeling an entire hospital, for example, it will apply to the ED, it will apply to the operating theater, it will apply to the inpatient units, and if you looked at the entire hospital as a whole, it will apply to that. Same thing in manufacturing. It will apply to your fabrication area, it will apply to your assembly area, it will apply to your testing area or your painting area, or the whole factory as a whole. And like I mentioned before, if you know any of two of the three systems, or two of the three terms in the equation, you can get the third, algebraically manipulating the law. Now, you got to be careful with it, though, because it only works for a stable system. So if you're going through a warm-up period or a cool-down period where when you're first starting it up, for example, it's not going to apply. It's also not going to apply if you do it for too short of a time period, or if the volume is too low, because you're not going to have time to let this hit. So there's not a mathematical law to say, okay, here's how you know when it applies and it doesn't apply. But what I did is I wrote a computer simulation model that you can play with to get a feel for how long it takes to actually apply, so that you don't overuse Little's Law, but you can still take advantage of it. If you don't have a long enough time period involved, the estimate's not going to be very accurate. So you could go ahead and take a look at the simulation model that follows, and I hope you'll enjoy it.